Hey guys, Mr. Riz here, and for this part, 412, we're going to do all three parts in one video here. They all kind of go together, even though they're broken into three separate things. It's just going to be good pacing. So you might get the first one done on the first day and have to do the next two on the second day, or you might get the first two and then do the third one. So it's all going to be kind of dependent, or you might have to do some work at home, something like that, but we'll have all three in this one video. Okay, so what we're going to be looking at is simulations to predict growth rates. So we're going to try to use the Netlogo web here, since that's going to be on a Chromebook, but if you want to use the desktop, you can. Our goals here is to use models and simulations to find trends in data, differentiate between correlation and causation, try to identify bias when deriving meaning from a simulation, and compare a simulated event with the real world. And so the materials we'll use is Netlogo. We're going to try the web as much as we can. We're going to see how well that works. Each time I make these, and then it seems like literally the next day the website gets updated. All right, so let's talk about growth patterns. In many complex systems, growth triggers a reason for study. For example, people study plant and animal growth patterns, bacterial growth in different environments, how viruses spread, and even how malware spreads on a network. So in order to study growth, researchers use simulations that model the behavior. So in this activity, we're going to learn about simulations that model growth. Okay, so what we're going to do here is we're going to go to Netlogo and we're going to look at the tree simple from the models library. All right, this program draws a special type of pictures called fractals. All right, a fractal is a shape that is self-similar. That is, it looks like it's shaped no matter how closely you zoom in. So for instance, a tree can be thought as a fractal because if you look at the whole tree, you can see the branches sticking out. But if you zoom into one of the branches, it looks like it's just a small tree with branches sticking out, and you can keep zooming in. And I'm sure you guys have seen like animated GIFs of fractals that are pretty crazy, things like that. So I'm going to go ahead, open up Netlogo web. Just this so we can split screen this here. All right, so in our models library, we're going to go through and we're going to find the tree simple. It's not working too well. Let's try it again. Netlogo web. I wonder if you can upload a file here. It's really weird. Okay, let me pause and see if I can restart. Okay, I guess I just had to go through and Google Netlogo web to get this to work. So in this model, what we're going to do is just click the Go Once button. So we'll set it up here, and then we're going to click the Go Once. And you can see we just had a very small split off into two branches. And what we're going to do is just click Go Once, and we got two branches off of those two branches. And then we got two branches off of every branch that was there. And we'll keep going, going, and going. You can see the branches kind of curve out as well. So not only do they branch off, they go through. We can keep going. Oh, I guess there might be a limit to the number of turtles that can be gained. There we go. We'll click setup, or did I just freeze that? I think I just froze it. Let's see if I can refresh that. Yeah, the web one might not be as best as we can. Okay, so let's go through. We might be able to go through this experiment here to, or just look at the map. Oh yeah, I clicked. I think what ended up happening, I kind of messed up. I clicked Go Once a bunch of times. You can see I got 32,768 turtles. It's probably a lot for the web. Yeah, there we go. Page unresponsive. Let's exit the page then. Can we refresh this here? Hopefully it will load up. All right, so yeah, we're definitely going to take our time because I think the web base will maybe just go through and corrupt this. So if we set it up once, there's just the one turtle there. If we go once, now we got two turtles. All right, if we click once again, the third iteration, okay, we got four. Hopefully you can start to see a pattern here. Go once, okay, we got 8. And so you can keep on going through and fill out this bracket. How many would we have after 5, 6, and 7 iterations? Okay, so what could you think would happen for iteration 8? Can you predict? And then tell me what the growth pattern is. So hopefully you can see that the 8th iteration here would be 128. And then can you make a growth pattern? Could you make a formula to state that? So if we wanted to know how many turtles there would be after the 30th iteration, what would be the formula we plug it into? So be specific when you look at the growth pattern. All right, so let's become familiar with this model. So once we click setup, we're going to experiment with the color ink. All right, so we're going to change it up a little bit higher, and we're going to go through. And you can see we get an arrow here. We get too long here, it's going to freeze or hang. And I didn't even notice it at 17. All right, so let's set up. Go once. All right, so after a while, okay, that changed. Okay, let's set up again. Make the color increment. Let's make it 0. Okay, so that just stays the same color each time. We make it a little bit more. All right, it's just slightly different. I guess if we make it larger, each color gets very different. Okay, so next we're going to increase the size of the world to allow for more room for the experiment. So we're going to add the following line command to the setup procedure. So let's copy this here. If the world is too large for your screen, we're going to reduce the value. Okay, so we're going to go to our code here, and we're going to go real world size. It's in the setup, right? Yep, in the setup procedure. Let's just do, maybe we'll do that. I mean, I'm sure it doesn't matter. All right, let's see if that made a difference. So we click setup. All right, yeah, it made it too large here for the screen here. So, oh, maybe what if I full screen? Yeah, it's still too large. So we might have to change those values here. Let's go to, can we even get to it? Yeah, I can go to the code. Maybe if we cut those in half. So just changing this to 100, 100, 100. I guess that's probably just X and Y locations set up. Still fairly large. All right, let's maybe go 75. It's still very large. Oh wait, I got to do recompile code. That's what okay, now, okay, probably have to go. I didn't see recompile code because it was being covered up. All right, 100, 100, 100, 100. Okay, let's recompile the code. Let's click setup, make it a little bit bigger. Okay, so now we got something that's bigger. Okay, so what we're going to do, explore how color is managed in the Netlogo, because it's important to go through this. So what we're going to do next is select tools and select color swatches. Actually, we cannot do this in the web-based one. Okay, so you know what I'm going to do here is I'm going to just pause the video. I'm going to do this on the desktop one. I guess that's what we'll have to do here. All right, so here we go. I'm going to change the resize world here on the desktop version. Let's do click setup, and there we go. Okay, now that's still a little big. I'm sure if I full screen this here, it's still a little big. I'm going to just adjust that just slightly. We'll do 180. So one thing you have to remember here with Netlogo is that you have to check the procedure, and you have to set it up, and then it changes. So, all right, that's a little bit better. Yeah, I'm sure if I split screen this a little bit more. Okay, so next what we're going to do is go through our tools here, and we're going to go to the color swatches tools, and we should see color swatches right here. It's right on top of it. To see what the color value names here. So we can see that 0, set color ink 0 and set color ink 55 is green. So we can see kind of the values or colors that get incorporated here that go through. So if you were to use, okay, basically, if you were to use 0 and 55, what colors would be black and green, right? Okay, so next, if you were to set color ink to 10 and ink color to 50, all right, what colors would be rendered in the tree? Okay, well, let's see. And we can always kind of predict this here. If we go ink color 10, we can change these numbers here. 50. All right, it'd be black and black, right? And we wouldn't actually, I don't, you can kind of, if you actually look really closely, you can kind of see that tree there. It's black and like very, 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 very dark gray. So we really can't see anything here. All right, next, what if we were to keep it at 10 here and set ink color to 105? All right, we can start to see it goes from dark, and then we can see the color changes here. So it actually kind of becomes a rainbow effect. So let's try to, think about, okay, looking at that, looking at the code, what does that ink color do? So we say for each turtle here, we create a turtle, we set color to ink color and X and Y. So we set the X and Y. So each one of those there, we're going to go through. So the new color, the color ink is how much it's changing by. So the color ink is how much it's going to change. Okay, this must be the initial color. So that kind of helps us out if we look at the color swatch here. So yeah, maybe it isn't so much starting at 0. Let's go back to these questions here and kind of re-answer that. Because now that we kind of know when we looked at the code, we can explain this. So if the ink color, the initial color was 55, it starts out as green and the color is 0. So it has nothing to do with black. It means the color is going to change 0. So if we start out here, this first question 3, so we might want to change this here. We're going to start out green and it's never going to change from green. All right, in this problem here, if we start at 50, it starts out as black and the ink color is 10. So it's going to go change by 10 each time. Well, changing by 10 each time, plus or minus 10, right, was just going to go 10, 50. So it's just going to be different shades of going through, green. Can we go like 0.5? Oh, we can get even closer colors. That's pretty crazy. That's cool. All right, so now if we have set at 105, 105 is, where's 105 at? It is right here. So we start out in this blue, and then we're going to change by 10. So we can go 95, 85, 75, or we can go the other way. I wonder if these numbers like repeat themselves as they get bigger than, what's 145? Okay. Can you guess what happens to numbers greater than 139? So what happens? We can kind of see here 139.9, what that looks like. But maybe we can go through and kind of set that up. So let's initialize the color. Let's start at 110. Set up. Go once. Oh wait, yeah, 110 is like black, isn't it? Let's do 109. And let's do 105. So as we keep going here, let's look at the color swatch to see kind of what happens. It's making a lot of turtles here. It's taking some time. Each time it takes twice as long to make. It looks like the colors are changing, but not too much. So I would assume that it would go to white. Let's see if we can just click go and see what happens here. There we go. Okay, we're going to let that run to see if that prediction is correct. All right, once you guys get that done, submit your Netlogo code. You're going to try to make these shapes here. You know what I'm going to do here is I'm going to adjust this because we're going to have to do this. We're going to have to go through and we're going to have to just make screenshots here. Okay, so let me pause the video and adjust this assignment. All right, so let's stop this now. Let's move on to part two. Part two is about viruses. So in contrast, the predictable like 2 to the n growth power is considered a growth model that is highly unpredictable because the spread of a virus, like the spread of a virus through a community, which we probably know so much about. So one thing about viruses, and I have this going. I wonder if I can quit this, discard that. There we go. Oh, that just quit the whole program. I'll start this up. What we're going to do next is to look at the virus model here. And so we're going to open up Netlogo. I'm using 6.0. I don't think it really will make a difference. Just don't do the 3D one. We're going to look for the virus model in the biology folder. So this here simulates the transmission and perpetuation of a virus in the human population. All right, so if you're colorblind, feel free to change the colors in this model to make something a little bit easier for you to do. But it will be like red, green, and gray. Those are the colors that are defaulted. Okay, so we'll pause this while this loads up. Okay, so we got the virus up here. So we're going to experiment with this model with the default parameter settings. What do the populations plot and the reporters tell you about the long-term growth of the virus? So if we just go default here, go, we can see kind of what happens. We can see the total population of people and how many people are healthy, how many people are immune, and how many people are sick. Okay, we can recall that we can change the speed here, so we make this go faster if we want. And we can kind of see what happens throughout time. And we can go through, we can run multiple runs, and we can click setup with the simulation to just restart this here. So it looks like it kind of goes through just cycles here. Each cycle, we get more healthy, and then, you know, healthy people go down. There we get a big sick population, and then more immune people. Let's set this up, maybe slow it down a little bit. So we start out, we have healthy people, then healthy people go down, we get sick people. And once sick people are okay, we get more immune people. Once we have more immune people, healthy people go up. So it's kind of like this cycle here where we go through. And sometimes we have big dips and small dips where we have a big group of very healthy people. Then after a while, after there's a lot of healthy people, then that means more sick people because there's less immune people. Then there's more immune people. So then we get more healthy people, you know, healthy babies, you can see, and then go through. So I guess the immunization doesn't transfer genetically in this simulation here. All right, so what does this tell us about the long term? Is basically there's a cyclical factor between, or a harmonious series between the two. So with this model running, we're going to change the parameters such as chance to recover and duration. So let's just change the chance of recovery to just 50%. Let's drop it from 75 to 50%. And we can see immediately there's a dip in the total population. And the total population just starts fluctuating a little bit more, right? Okay. Or we could change the duration. Maybe make it from 20 weeks, make it to 35 weeks. What does that do? Okay, so now this becomes something that is really affecting the total population. Seems like the total population is having trouble recovering from this. So how do you determine if the virus eradicates or completely destroys the population? So if there's a chance here, so what parameters would simulate this? So could you find something that would just completely destroy the population? So kind of mess around with this. Maybe if we make the chance of recovery really low, 10%. We can go through that and see kind of what happens there. All right, so 10% recovery means the population goes low. But once it's a smaller population, you know, you're kind of social distancing from each other. And so you're less likely to commute the virus to each other. So it kind of remains as a series. So maybe if we make the duration even longer, so that the virus sticks around longer and people can spread that faster. And let's see. We're just going to be changing those two parameters there. maybe, so I guess maybe let's go chance of recovery 0, where if you get it, you don't recover. All right, well, I got to the point where I had nobody, now there's nobody infected, nobody's immune, so let's set that up again and try to do the other way. Okay, now everybody's infected. There's no chance of recovery, everybody dies. So it'd have to be something like that, where the duration's super long, where it basically doesn't go away, and then the chance of recovery is really low. All right, so let's predict the spread of the viruses in this complex model. What are some inclusions and exclusions in this model? So let's, we got to think about, what are things that exist in real life that could happen that don't actually happen. I think we can think of some real life examples here. In this model here that we had where it's really bad, we don't have people self-isolating. So we just have, people, if you look at this, we click setup and go. People are still moving around day by day. They're not stopping. So we could go through and maybe change where the people just don't touch each other. So I guess that would affect the effectiveness, the infectionness, but we can go through. So those are some things we're getting out, some exclusions. Other exclusions, maybe there is a, the virus goes away and we get an immune system built up, or we have a vaccine that gets distributed. Some inclusions here. So what's being included in here that is not in unlike the real life? So one thing about this, all these people are the same. So we could talk about, certain people might have a predisposition to it. So we're just trying to think of things that, this model does show, but it doesn't actually show everything. So this would be like a normal city or something like that, just day-to-day living here, where people don't stop or change any of their social behaviors. Okay, so let's modify the model so that one simulation parameter, and then we're going to change the length of time the person stays immune. So let's go through this one here. We're going to modify the model. We're going to rename the current duration variable to something more meaningful, so just as like virus duration or sick period. So let's go through and let's edit that to, let's call it sick period. Okay. So we're going to determine the current immunity duration from the code. Okay, so we go through here. If sick time is greater than duration, so we're going to say sick period. All right, we're going to add a parameter so that part of the interface and its value is changed. So we're going to choose the values that are realistic to you. Okay. So what we want to do here is to go through and to change. So right now it's like if the sick time is greater than the sick period, else if we pick a random twice less than 100, if it's less than the chance of recovery. So we're picking a random number from 0 to 100. If it's less than the chance of recovery, we become immune, else if they die. So they either recover or die. So we're going to change the parameter so it's part of the interface value. Okay. Actually, you know what? I think we're doing something. Let me double check, make sure this is not what we're doing. Okay, so sorry, I guess I was thinking too much about what's going on here. What we want to do here is to modify the code so that the person stays immune the whole time. So right now, if we go through here, we've set up, we click go, we can see like the amount of people get immune and then they lose immunity. I guess we're kind of maybe thinking about they go through, but we want to go through and change it so they just stay immune the whole time. And we're going to go through and kind of change it. I guess we didn't have to have this set up. I totally restarted the code here. So we want to rename some things here, and we're going to determine the current immunity duration from the code. So let's see, immunity duration is how many leads, and that's the global variable right at the beginning here. And so you know what I might do here is just highlight this here. Control F. Let's find them. So, okay, right here, we have to become immune. We get sick is false, sick time is 0, set remaining immunity to immunity duration. All right, so right here, set immunity duration 52. Okay, so what if we just get rid of that, right? So we're going to add, so determine the immunity duration. So the immunity duration, which is set up here, as a global variable that's going to be used is equal to the remaining immunity. So right here, the immunity duration is 52, right? We set up the constraints. So we say it's going to be 52 weeks. You're immune for 52 weeks. Let's make that something more practical, right? That's just for 1 year, right? What if we make that equal to, well, 52, we can times that by, I don't know, 100. Make that worth 100 years. Oh, can we not do that? We gotta do space. Oh, wait, they have 52. Oh, what do they say right here? 2600. Well, let's just do 5200. All right, let's go through our interface here. Let's set up and see what happens here. See if we get more immune people. So definitely, okay, our immunity's going up. It's going up. It's kind of peaking because the virus just went away, right? The immunity goes through. So, yeah, what I want you guys to do here is to go through and change the code. Now, maybe we can go through and make that actually like a slider, right? We could go through and change that so we can see the immunity. Now, what ends up happening here, I think some people, the number of immune go down. Is our population going up? Or is our population set to 300? It seems weird that the immunity percent is going down. Maybe people just die after so long. Let's make this go way faster, see what happens. Whoa. Okay, so yeah, this is interesting to see. This is several hundred years later. So people must just die. And then, right, there's a big cutoff here where like everybody who was immune just died and then that's gone away, which kind of makes sense. Like, you know, I don't know if you guys ever, like theories like the Spanish flu was actually around like in like the Ice Age or something like that. And because of global warming, they suggest like that virus was released because they can find bacteria and other viruses that are frozen and they can bring them back to life from them being thawed out from the ice. So just weird things like that make you wonder here. Okay, so once you guys get that done, submit your HTML if you're using on the web or go through. So let's hypothesize this. Given the following parameter, a virus has a 95% infection rate and a 5% chance of recovery. We could probably set that up, couldn't we? 95% with a 5% chance of recovery. So very infectious, but very small chance that you will survive. All right, and it has a 12-week duration period during that time, and only 6 months immunity for humans. So let's change that to 6 months. Let's say that's just half a year. So let's say that's 26 weeks here in our interface. How long do you think the virus will last if we start out with initial population of 150 people? So we can set that up and just kind of run that here, and we can see how long will happen. So I got a lot of people that survived. All right, so maybe let's go through. Let's go, maybe my model is kind of messed up. So let's discard, let's open that back up again. Let's go through. So this is kind of nice. We can use things like this where we have an extremely infectious disease that is extremely deadly, has a 12-week duration and only 6 months. So if we go to our code here, we're going to change that to 26. Oh, I forgot to check that interface. Let's set it up. Go. All right. How long do you think people last? So answer in years. I'm getting people just live forever, right? 95% infection rate, 5% chance of recovery. There's a 12-week duration and 6 months of immunity in humans. Yeah, I don't know. someone's, every time I'm running that here, the setup goes slower. Oh, maybe the chance of recovery should be higher. Yeah, I don't see that. Okay. Well, maybe I have to change it. I think that one here should be go through. I'm just going to look at project lead the way here. We're going to pull that up real quick here. Maybe I'll take that question off. Let's go through. They said approximately 2 to 10 years. I'm not getting that same response, but you know, project lead the way has been very iffy on this lesson here. All right, I got to stop this video here. We'll do a second part for part 3 when we're looking at computers. See you guys in a minute.